a special lecture on ML Type Inference. This is the first video of the lecture about the lecture and history of ML Type Inference. This is Atsushi Ohori's computer science channel. I'm Atsushi Ohori. Before giving the lecture, I give some meta information. As I said, this is a computer science channel of Atsushi Ohori. Actually, this is an English translation of Keisan Kikagaku channel. Keisan Kikagaku is a Japanese terminology for computer science. And this channel provides video lectures in computer science, which are graduate and undergraduate level courses, mainly on programming languages, functional programming, type theory, and systems, computer architecture, and operating system. I have been running this channel for about 1 year. So far, the videos are given in Japanese, using my Japanese textbook. After 1 year of running this channel, I thought that it is a good idea to extend the target audience to anyone in the world interested in learning computer science. So I try to provide videos in English. So this special lecture is the first experimental video lecture in English on ML Type Inference in the field of type theory. This is actually a translation of my past video lecture in Japanese. So there is some restriction. That the obvious one is that the textbook is currently only available in Japanese, and the lecture contains citation of Japanese literature, which I translated. I started the lecture by giving overview of the lecture and also describe my motivation. Overview that this lecture is to learn ML style type inference, underlying polymorphic programming languages such as standard ML, OCaml, and SML#. Well, if you don't know SML#, don't worry. I will have another occasion to introduce this language. I note that ML doesn't stand for machine learning, but for meta language. And my motivation of organizing this special lecture is the following. So my observation is that existing textbooks and tutorials usually explain the following. An ML type inference algorithm infers a principal type of an expression. This is indeed intuitively plausible and nice. However, this explanation is technically imprecise. To my observation, furthermore, ML type inference is rarely given rigorous theoretical treatments in textbook and lectures. So this is somehow unsatisfactory, and my motivation is obviously to improve this situation. So goal of this lecture is to provide rigorous understanding of ML type inference through, firstly, thorough treatment of the implicitly typed lambda calculus and its type inference problem. This is the basis of understanding ML. And then analysis of ML polymorphism and type inference algorithm W, and development of a new framework for ML polymorphism and type inference. So this target audience. So this lecture is probably a graduate level course containing mathematical development. However, I organize this lecture self-contained so that it is suitable for anyone with basic mathematical training. So this is the overall nature of this lecture. So this is a free lecture open to everybody. So I describe my profile for your information. My educational background. I received a BA in philosophy from University of Tokyo, and then PhD in computer and information science from University of Pennsylvania. Here's the employment I have so far: engineer and researcher in industry, and then postdoc researcher funded by British Royal Society, and then associate professor, Kyoto University, professor Japan Advanced Institute of Science and Technology and moved to Tohoku University. Until 2022, this is a national university, government-funded university, which has fixed, every government-funded university has a fixed retirement age, which I have reached, unfortunately. Well, fortunately, I'm not sure, but now I'm Professor Emeritus at Tohoku University. So I have been doing research on type systems and programming languages, focusing on ML type inference, well, and many other aspects, but mainly on programming language, especially ML. Recently, I am interested in non-Cartesian semantics. Don't worry about this. I will try to find another occasion to explain this. And also, I have been developing with my colleague SML Sharp language. So I can say that I am one of major architects of this programming language and co-developer. So this is my profile. For short, I think I can say that I am an expert in programming language type theory, type inference, and ML. This and the following several slides, I describe my motivation. I elaborate my motivation of this lecture. So why a special lecture? First point is current understanding of ML type inference. I commented the following. It is often explained that ML type inference, ML infer, is a principal type of an expression. This is technically imprecise. I said this way. So let's see some example of explanation. Here is probably the most well-known explanation I took from Wikipedia on type inference. In type inference page, there is a paragraph, principal type, and it explains the following. Principal type, the summarizing all possible types an expression may have. The order, this is the instantiation order of polymorphic types. The order guarantees that such a summary exists as the most general type of the expression. Probably this is the standard and most common explanation of ML type inference. Another example is I took from Japanese textbook. After explaining example like the identity function which ML compiler infers this type information, where this prime A apostrophe A is a type variable pronunciated in ML terminology, ML jargon, alpha. So alpha arrow alpha is a type of identity function. This is a type variable. So after explaining this example, the textbook says this most representative type of an expression is called a principal type. This is Japanese textbook by Professor Atsushi Igarashi, and these are indeed intuitive and quite nice properties if they are well grounded. Unfortunately, I would say there seems to be no theoretical basis that establish these properties. That's my observation, first observation. Second point of why a special issue, that is current explanation of ML type inference. So this is my summary of my understanding. A natural definition of a principal type of an expression is impossible under the conventional type system. Conventional type system means the type system proposed by Damas and Milner, which has been used widely. So the standard, well-established type system. Under this, there is no natural notion of a principal type of an expression. So probably reflecting this, some assumption such as below is presupposed. The typical assumption is this. It is customary to define a type inference algorithm as a function to take an environment of variables that are defined before. So this is again Japanese literature for general audience by Professor Eiichiro Sumi, published in Nikkei Cross-Tech. And also, after the textbook definition of the principal type, the textbook stated the following. So this is a technical definition that supposedly elaborate the intuitive definition of a principal type. So it says immediately after the intuitive definition the following: a principal type of a typing environment gamma and an expression E is a pair S of substitution and a type tau satisfying two property. These two property, first is this one, and second is a little bit more complicated. For any S prime gamma turnstile E colon tau prime, there exists S double prime such that. So this supposedly precisely defines the notion of a principal type, which is a type that represents all possible types of an expression. However, you can immediately see that where this gamma comes from. And also, there's something unnatural that this should be a definition of a type, right? Principal type, but type why a principal type is a pair. So you can see that at least this is a complicated definition and doesn't correspond to the intuitive definition of a set of all type, or type that represent all possible type an expression has. So presenting these complicated definitions without technical justification or explanation doesn't seem to contribute to a proper understanding of the essence of ML type inference. That is my observation, my understanding. So this is the second point of why a special lecture. So why a special lecture? Next point is understanding the essence of type inference. So any study, in any scientific study, you must start with the basis. Skipping that basis, it is difficult to go into the higher level of understanding. So let's briefly overview the basis of type inference. In the simply typed lambda calculus, this is a basic system, the most basic system. Any well-typed expression has a principal typing. This is different from principal type of an expression I explained before. A principal typing has this form of judgment. You have expression here and type and assumption. So this reads the following way. Under this assumption is assumption on free variables of the expression. This example expression is x applied to y. Both are variables. So variables are assumed to have some type. So typing environment, type assumption, x is type T1 arrow T2 and y is type T1. Under this assumption, x applied to y has type T2. So this is a straightforward typing. And you can observe that any types this expression has is an instantiation of this type. T1, T2 are type variables, so you can instantiate to any type. So by instantiating some type for T1 and T2 and add some irrelevant assumption in this, for example, Z or W in this typing environment, you get a typing of x and y, x applied to y to some type. So the property that any well-typed expression has a principal typing is literally straightforward property. So principal typing, as the name suggests, represents a set of all typing of E. This is straightforward, nothing complicated. Right? So this is a basis of any type inference problem. So type inference algorithm for this, in this simple basic world, simply takes an expression and returns its principal typing. So I will explain later in this lecture, of course, that and in that some part of this lecture we go through the detail of this type inference algorithm. But let's assume that, let's call this type inference algorithm PTS. Then PTS takes expression, for example, in this expression is given to this PTS algorithm. Then the algorithm returns pair of typing environment and type, and under this xy has type t. So this algorithm takes expression returning principal typing. So its correctness proof is easy to follow. There is one technically elaborate tool called unification, but once you understand unification, the correctness is almost straightforward. Of course, you need to do some mathematical proof. We will study this aspect, but nothing complicated. And of course, type inference algorithm also infers typing environment gamma as well. So no need to give it as an argument, right? So it's straightforward. Infer gamma and types. Right? So as a note, this is a Hindley part in the so-called Hindley-Milner type inference. So ML type inference is often called Hindley-Milner type inference. This terminology is a bit imprecise. Hindley-Milner, a different aspect. Hindley developed this basic property, and Milner did something more, something else about ML's polymorphic let expression. So this is a basis we must understand first, right? So in the special lecture, we go through the details of the basis, including the soundness and completeness of type inference algorithm. I already said, skipping this basis and studying complicated definition of principal type of an ML expression directly may not lead to an understanding the essence of ML type inference. So next point for our special lecture, that is the analysis of ML type inference. Once we acquire the background, that is the basis of type inference of the simply typed lambda calculus, then we go into understanding ML polymorphic definition. So this is an informal explanation about the subject we are going to study through this lecture. So this is informal, but let's go through this informal explanation. So ML extends the lambda calculus with let definition. So let definition, as a definition, it bind variable. So let variable is used polymorphically based on the principal typing of the bound expression. This is intuitive understanding, informal understanding. Let's see simple, straightforward example. So this is an expression. Let large x equal lambda x dot x. So this is the identity function whose principal typing we understand that it's alpha or alpha, and this x is used in different instance for each occurrence. So this x applied to small x, this x applied to small y. X and y are independent, so infer different type variable t1 and t2, and this x and y are identity functions. So in this occurrence, this large x is used as t1 arrow t1, and this x used as a t2 arrow t2, and then result is t1 cross t2. By the way, this x and this x is nothing to do with each other. So this is a bound variable, and this is a free variable, as the usual convention goes. Right? So this is intuitive understanding about a simple case of let definition. The polymorphic type of a let variable is given through this term. and is not the subject of type inference. That is one part of the understanding. So from this definition, you can expect that if we could separate types to be inferred from polymorphic types of let variables, then we could extend PTS, as I explained in the previous slide, that takes an expression and infer both typing environment and type, principal typing to ML. Such separation is, however, not simple, due to the property that this X is bound to expression which contain free variables. So let's look at this example. Different from this X equal lambda w dot w applied to X, and X is a free variable. And this X is used in different way, in this case applied to Y and applied to Z. So in this expression you have three variables, X, Y, Z, and suppose X is T1, and this Y become W, which is applied to X, so Y is a function taking X, same as Z. So you should have this kind of typing. Y is a function from T1 to T2, and Z is a function from T1 to T3, and resulting in T2 cross T3. So the complication is that this type of X intermixes with polymorphic part and monomorphic part. So this is a Damas-Milner type system. The current ML type system by Damas-Milner interleaves monomorphic types to be inferred with polymorphic type schemes. The complicated definition of principal type of gamma and E, as I briefly explained, describes the desired property of Milner's algorithm W under this Damas-Milner type system, which interleaves these two aspects. That is a major complication. So this suggests that we may have a new framework that somehow separate from these two roles and then make things more simpler. So that is agenda we are going to take. Next point is a new framework of ML type inference. I briefly suggested in the previous slide. So this lecture also contains a new framework. So this is a strategy we take to develop such a new framework. So develop a type theory and type inference algorithm in the following steps. First step, we develop a type theory for a subset of ML called lambda def, where polymorphic types of let variables are separated from types to be inferred. We then construct a type inference algorithm that infers a principal typing, same shape as in PTS, under this type system and show its correctness. The second step is to establish a translation method from the full ML to this restricted system. Show that the type system and type inference algorithm of ML obtained from the translation are equivalent to the Damas-Milner type system and the Milner's algorithm W. So this is an intuitive overview of the last part of this lecture. So this part is a new, as I said, that can't be found in existing literature and textbooks, including mine, of course, because in 1997 this isn't existed, right? So, well, my intention is to make the lecture note available to the audience in some future, in some way. How or when are not yet decided at this moment. So at the beginning of this video, I explained that this video is the first of the series of programming language theory series. this series takes the title from the title of my textbook. The video series including this special issue are based on the textbook that I published. Unfortunately, this is in Japanese only from Kyoritsu Publishing. The original hardcover issue is 1997. That same content is republished as paperback recently, 2019. So this textbook is on type theory of 4 programming language. It's rather old, 1997. But even today, I think that this is one of few available available textbooks that contains a detail of type inference of lambda terms and ML. Well, on request, I might make an English summary or English version in some future, some way. So far is a rather long overview of the lecture. Now, as a technical contents, I first review history of ML type inference. The first systematic framework for type inference of functional expression is by Hindley, the principal type scheme of an object in combinatory logic, 1969. In this paper, Hindley showed that the principal typing of a combinatory term, which is an expression made up with S and K and atoms, variables, and function applications, can be computed using Robinson's unification algorithm. So this combinatory term doesn't contain lambda abstraction. However, in this paper, Hindley showed a theorem that in the combinatory logic you have a deduction theorem which simulates lambda abstraction, and that simulated term has the same typing scheme of lambda abstraction. So we can regard this as a principal typing property, established a principal typing property for the simply typed lambda calculus, untyped simply typed lambda term. So this is the first one, Hindley-Milner's Hindley part. And then 1978, Milner proposed algorithm W, the theory of type polymorphism in programming. In this paper, Milner proposed the type inference algorithm W for expression with ML's polymorphic let construct, and shows its soundness with respect to the denotational semantics. It showed the completeness of type inference, but with respect to type assignment system, which is not quite yet a logical typing derivation system. But this is the beginning of ML polymorphic typing. So after Milner's proposal of algorithm W, Damas and Milner proposed a polymorphic type system of ML. In this paper, principal type schemes for functional programs. And in this paper, they define a polymorphic type system of ML with polytypes. They call polytypes, which is a second order time including for all binding of type variables, and two rules. One is to generalize type variable, and the other is to instantiate type variable. So this is a logical derivation system, derived typing, and typing include polymorphic types. And this paper claimed that the algorithm W is complete with respect to this polymorphic type system. Later of this publication of this paper, completeness proof is published in this Damas PhD thesis, 1984. This has been the only published proof for some time. Now I think there is some proof available in textbook and so on, but for some time this is the only proof available. And There has not been a journal version of this conference paper, but this is just a comment. Now, if you go through this proof, you will find that the completeness proof of algorithm W is a complicated one involving a number of lemmas. So next aspect of history of ML type inference is principal typing problem. As I said, it's complicated. Proof is complicated, and indeed it is complicated. And the major source of complication, the major obstacle in establishing completeness property just by induction of term is the lack of principal typing of expression containing free variable having polymorphic types. So this can be regarded as principal typing problem. And of course, this has been noticed in literature. There's few papers. Most known is this one and this one, where polymorphic type systems, including the Damas-Milner system, there are no principal typing property. So this is additional information about ML type inference. That is surveys and tutorials on type inference. There are many, I would say, several choices on tutorials and textbooks on ML type inference. Among a number of choices, I recommend this one, Potier and Remy, The Essence of ML Typing. Well, there's one comment. This survey is comprehensive and well written and precise, reliable one. This survey adopts HMX approach, which solve type inference problem not directly by unification but by generating constraint sets and computing its solution, their solutions. But as I said, this is comprehensive and easy to read and reliable, so I can recommend. One additional note about this constraint-based type inference. HMX, which is I think best known for constraint sets generation and solving solution to solve type inference problem, this approach. So this paper, this is Odelski, Zaltzman, and Vera. This is probably not the first one on this approach. And I would say that the first proposal of a constraint-based type inference approach is probably this one, Suzuki, Norihisa Suzuki, Inferring Types in Smalltalk, published in 1981, which is not often cited. For some reason I don't know, but this is just a side comment. So lecture plan after this first video. So there's 10 videos, and the first one is this one. And now we start by inductive definition of languages. And this policy of this lecture is to understand rigorously and easily, of course, and so we start by the basis, start with the basis, that is the definition of language. And then we do various property by induction, so third step is to prove by induction and induction principle. And then we go through simply typed lambda calculus, implicitly typed lambda calculus, and understand principal typing and typing derivation system, and then we go into the PTS algorithm and show its soundness and completeness in detail. This completeness uses unification, so I also treat unification algorithm and correctness proof in detail, and then go to the ML type inference and reconstruct some part of ML to account for better understanding of ML. And I define lambda def I explained, and then define ML type inference through the translation of this system. So this is our plan. So this is the end of this first video.